like negative wrapped convolution. Do you understand why that works? Like I understand if you just like follow the thing, you come up with the right answer, but do you understand like why it doesn't alias? It just seems like some random twiddles were changed and then it works.
Why it works in the structure, or
like why is there a way to understand intuitively why it doesn't alias even though there's only 4 of them instead of 8? Like I understand that if I go through the algorithm of the thing, you get the right answer then. But I don't understand why it doesn't alias.
why it doesn't.
Or like, because when you do it without negative wrapped convolution, you need the 8 point, because when you multiply it, then when you multiply 2 4-point sequences, you get 7. So why does the negative wrapped convolution only work with 4, or work with just 4 instead of 2?
Okay, well, I heard some discussion about negative wrapped convolution. Do you want to ask your question?
Yeah, I guess. So when I was going through the homework, I guess I understand that the number theoretical transform, the negative wrapped convolution version works with only 4 points, but I wish is there like some sort of intuitive way of understanding why it works and doesn't alias, even though when you do it with the normal NTT, you need to pad it to 8?
Yes, yes. So the question was why the negative wrapped convolution works intuitively. I mean, of course, you all understand that if we computed 2n minus 1 points and then add the last n minus 1 back to the first n minus 1, that should work. And so that's happening automatically through the negative wrapped convolution. And why is that happening? And well, that's what I proved last class, right? So what I showed by computing this AK tilde and BK tilde, that's the entity of AI psi to power I and B psi to power I. And if you go through the math that I did here, and then the expression that we got, which is here, and that psi to power n is minus 1, so that's why that became minus. So that's really why it automatically makes that minus and subtracts, and that's why it works. You have to go through that math a little more. Okay, yeah. Good question to ask. Very good question why it works. Any other questions before we start? Okay, so I was kind of reviewing last time how to do the negative wrapped convolution using the entity and how to implement that using n-point entity. And what would those structures look like? So that's what we were talking about. And so so we started last class by defining AK tilde, that's AI psi to power I times omega to power ik, and then describing that as sum of two sums I equal to 0 to n by 2 minus 1, the even terms and the odd terms. Okay. So we already talked about that. So then from that, so that's the first k coefficients, 0 to n by 2 minus 1. For the next ak plus n by 2, and once again, omega is the nth root of unity, and omega to the power n by 2 is minus 1. And so this whole thing plus this twiddle times this whole thing is AK tilde, and if you make that plus a minus, and that becomes a k plus n by 2. Okay, so maybe, okay, and then I was talking something about identity, and we didn't really complete that fully. So we started working on that, right? Okay, so these are, okay, so let's start from this point. So let's start from these equations here. So we'll start from these equations. So ak tilde and ak plus n by 2 tilde. Okay. So ak tilde is equal to L is equal to 0. I think what I could do. Okay, all right. So let's start from the very basic definition. AK tilde is equal to I equal to 0 to n minus 1 AI psi to the power I omega to the power ik. Okay. So before I even proceed further, I think what is useful, I think, so that's really the pre-processing step. And so if you think about the standard entity matrix, okay, so if I define AK is equal to sum of I equal to 0 to n minus 1 AI omega to the power ik. So the standard entity matrix, let's call this W, probably doesn't matter a lot. So that I can write as similar to FFT matrix, right? So for 4 point, that would be omega. So all we are doing is replacing the complex exponential W e to the power minus j 2 pi by n by the nth root of unity omega squared omega cube omega squared omega to power 4 omega to power 6 omega cube omega to power 6 omega to power 9. Okay, so that's the standard entity matrix. So the negative convolution entity matrix, so you can then say that, okay, cap A is this times lowercase a, the vector. So the negative wrapped convolution entity matrix. So if I write this equation here by let's call it W prime. It is always nice to think a little and find good notations, but let's just take W prime. And so essentially what I am trying to say is that if I bring this psi term inside this W, so I then want to express, okay, so here A0, A1, A2, A3 would be W times that vector A0, A1, A2, A3. Okay, what is W prime? So W prime, A0 prime, A1 prime, A2 prime, A3 or tilde, A0 tilde, A1 tilde, A2 tilde, A3 tilde, let's call this W tilde then, is equal to W tilde times A0, A1, A2, A3. So the question we are asking is, if I have to incorporate the psi inside this entity matrix, what would that be? So essentially this, all we are doing then is this A1 was psi 1, so anytime we take the first row, so think about what would be this quantity. I am kind of skipping a step, but so if you think about what this would be 1 psi squared psi cube 1 omega psi omega squared psi q squared omega cube psi cube 1 omega squared psi. All I am doing really second column I am multiplying by psi, third column by psi squared, fourth column by psi cube. And you can see that if I take this multiplied by A0, so 1 plus I times A, 1 times A0 plus I times A1 plus I squared times A2 plus I cube times A3, and that's really what is A1 or A0 tilde. Okay, second row, second column, 1 times A0 plus omega times A1 psi plus omega squared times A2 psi squared plus omega cube times A3 psi cube. And so instead of having psi squared psi cube here, we put them in these columns. Okay, is that making sense? Okay, I see some nods, that means it is making sense. Good. So there are some fundamental differences between the W and the W tilde. Okay, so the W is a symmetric matrix. W tilde is not symmetric. That means, so because W is symmetric, if we derive the structure such as decimation in time, entity or FFT, doesn't matter, we could transpose that to get an equivalent structure, and we cannot do that here. So there is no way, so we cannot simply take a negative wrapped entity convolution entity structure and transpose that to get another equivalent structure. That is not possible because this matrix is not symmetric. If I transpose the first row, 1 psi squared psi cube is not 1 1 1 1. So that's kind of something to keep in mind, very important property. So the whole process of transposing one FFT structure to get another equivalent FFT or even entity doesn't really apply here. Is that making sense? Okay. So that's something good to remember. Okay. So, however, the okay, well, I will come back to that. So let's go back to our let's see. So let's go back and spend a little time. We did derive those equations, but I think the structures probably didn't. Yeah. So yeah, okay, we did. So let's go through this derivation again. So dividing this by two parts, we got a. Let's see here. Yeah. Okay. So these parts. Okay. So that's fine. So so if we take these two equations, ak tilde and ak plus n by 2 tilde, and then okay, so if we take this this equation here, so we compute. Okay, there is. So remember, omega is psi squared. Okay, so omega. So this would be psi to the power 4lk plus 2l. 4lk plus 2l. Okay, I think it would be good to write down Okay, let's write down this equation. A k tilde is equal to summed over L equal to 0 to n by 2 minus 1 a to L psi to the power, okay, psi to the power 4lk plus 2l taken outside a bracket 2k plus 1, 2l taken outside a bracket 2k, 2l times 1. So that's that part plus omega is psi squared, so that's psi to the power 2k, I should say from 14.7, okay, psi to the power 2k plus 1. Same thing here, 2lk, 2l. And ak plus n by 2 tilde is equal to same thing minus psi to the power 2k plus 1, same thing. Okay, so that's good. Okay, so now, so think about psi as the new twiddle factor and think about this as kind of a 4 point, some kind of entity, some kind of, not the entity the way we define here, but some kind of entity like we define in this W tilde. So then we can say, okay, so we take the even 0, 2, 4, 6, compute this some kind of 4 point entity. Again, I say some kind because it's not exactly the entity equation given by this. And then some 4 point entity of the odd, and then that's the twiddle. And then plus minus will be the butterfly. Okay, so what are going to be the twiddle? K equal to 0, psi to the power 1. By the way, n is 8, psi really is same as psi 16. So this is the 2nth root of unit. I'm not writing psi 16, but that's what it is. Psi 16 to the power 1 if you want to think about that. K is equal to 1, so these are k equal to 0, 1, 2, 3, psi 16 to power 3, 5, and 7, and then, so those are new twiddles, and then we have the butterfly. Okay, so that is our so-called DIT decimation in time entity, decimation in time entity for the negative wrapped convolution. And what is inside these 4 point structures? That's really these equations. So if you think about what is inside the 4 structures, so that would be A0. So this, if you think about what is in this A0, so this one, take the even of the even, A0, A4, and then A2, A6. So these are the even, and then compute 2 point butterfly, 2 point entity, and then, so now these are going to be, so for this part n is equal to 4, so this will be psi 8 to the power 1 and psi 8 to the power 3. So the psi to the power 2k plus 1, k equal to 0, k equal to 1, and that's going to be inside Okay, so this is going to be inside each box here. Okay, inside this box and this box, that's what is here. Now what is then going on in n equal to 2? So for the 2 point, and if you just write down, so there is no summation involved. So there is just no summation, right? So just n is 2, 2 by 2 minus 1 is 0, so that's just, this whole thing is n equal to 0. So if you write down the equation for n equal to 2, then a0 tilde will be equal to a0 plus psi 4 a1 tilde is going to be a0 minus psi 4, n equal to 2, psi is fourth root of unity. So that's really the definition of, that's what, if you substitute for n equal to 2 in this equation, there is no summation involved, just one term, L is 0, psi to power 0 is 1, psi to power 0 is 1, psi to the power 1 minus psi to the power 1. Okay. So that's the 2 point structure. So inside each of this box, what we have is okay. So this goes in each box here. This whole thing goes in each box here. Okay. So that's kind of how we derive the decimation in time. And if we put all these together, if we put this inside here and put the whole thing there, I can draw the complete DIT. Those are the pre-multiplications for the 2 point. Okay, so those are all 2 points placed there. For the 4 point, we have psi 8 to the power 1 and 3. So now we completed the top 4 point. Okay, and we completed the bottom 4 point. So we have completed this and that and these parts. Okay. Okay, that is the complete 8 point entity for the negative wrapped convolution. 8 DIT entity, and the diagram that we have given you in your homework is a redrawn version of that in a way that this A0, A1, so you might see, so what you are seeing is really same as this diagram, it's just redrawn with the inputs placed in order. There's nothing new about what you are seeing there. So, so that's something to think about. So you cannot transpose this to get another equivalent structure. So how do we really obtain identity? NWC, negative wrapped convolution. So first of all, let's think about what is exactly, so we started with the equation last time, this equation here, PL tilde, which was n inverse of that thing, that's really the standard identity quantity. We can express standard identity matrix. And then if you think about this post-processing, that PL is psi to power minus L times this whole thing. Okay, so so we can write down PL, or let me write down as PI is equal to n inverse psi to the power minus I okay. So what really are we trying to accomplish? So the traditional W inverse, this is the, so by the way, don't worry about n inverse. So that's the scale factor, let's not worry about it now. So what we are more interested in is how do I incorporate this psi inside this entity or identity. So if you think about what I could do, so if I define that W inverse for a simple example of n equal to 4, omega inverse omega to power minus 2, omega to power minus 3, minus 2 minus 3, minus 4 minus 6, minus 6 minus 9. Okay. So, so what is our intent? Our intent is to compute the entity, identity matrix, and then multiply by this psi to power minus I. So in a way, I can define W tilde minus 1, W tilde inverse. If I was going to compute, so I could compute some P0, P1, P2, P3, but what I want to compute is P0 psi to power minus 1 P1, psi to power minus 2 P2, psi to power minus 3 P3. And that's really what I'm trying to compute. And what does that mean? How do I modify this inverse entity matrix, the standard matrix, so that I can capture the effect of multiplying by these things, the so-called post multiplication. So if I want to put these three quantities inside this and call that W tilde inverse, then I can say, okay, the P vector is going to be this matrix times the P tilde vector. And I don't have to worry about that because that's now part of this W tilde matrix. Okay, so what would that look like? So, so that matrix would look like Okay, so P0, what would P0 be? P0 would be, I should say that these are tilde though. These are tilde. These are, no, okay. So let's multiply this by, so this would be P0 psi to power minus 0, which is 1. So this would simply be P0 tilde plus P1 tilde plus P2 tilde plus P3 tilde. Okay, I am not taking into account that scale factor, don't worry about that. P1 when I is equal to 1, psi to the power minus 1. So this would be, so initially I would have that matrix P0 tilde and so on. So this would be 1 plus omega to power minus 1 P1 tilde plus omega to power minus 2 P2 tilde plus omega to power minus 3 P3 tilde, whole thing multiplied by psi to power minus 1. Okay, so what does that really say? So the elements, the first row will be all ones. So think about this multiplied by this vector P0 tilde, P1 tilde, P2 tilde, P3 tilde. The next row P1, everywhere I have to multiply by psi to power minus 1. Take the second row, multiply by psi to power minus 1. For the third row, P2 would be psi to power minus 2, multiply everything in this third row by psi to power minus 2. And for the last row, multiply everything by psi to power minus 3. And that's our modified entity matrix. Is that making sense? All right. Okay. So that's really what we are doing. We, instead of just multiplying or using this entity matrix, we just modify this I entity matrix. Okay. So now, if you look at the W tilde and the W tilde inverse, what do you see? W tilde inverse is transposed version of W tilde. So if I transpose this, if I go through two steps, transpose this entity, modified entity, and then replace every twiddle factor by the composite. So transpose this, the first column 1, 1, 1, 1 becomes first row. Second column psi, omega psi, all those, and inverse those, take the complex, well in this case not the complex conjugate, but take the inverse modulo q. So then we get omega, psi inverse, omega inverse, psi inverse, all those. So now in fact all I need to do to compute the I entity is take this 8 point whatever structure we derived and just transpose that. If I just transpose that, then I get the modified entity structure. Just transpose this structure, that's all I need to do. Just transpose this entity and conjugate, so replace these by the way, one other thing that you probably noticed, that psi 8, if I want to put this all into base 16, psi 8 to the power I would be psi 16 to the power 2i. So this would be psi 16 squared to power 6 squared into power 6. And this psi 4 to the power I would be psi 16 to the power 4i. So this would be psi 16 to the power 1, psi 16 to the power 4. So you could, it doesn't matter, you could write this as psi 8 squared, psi 16 to the power 4, it doesn't matter. So if I transpose this, what will happen? The left side will be in place. These will be 0, 1, 2 in order, and then go through that minus, minus 3, minus 5, minus 7, minus 1, minus 3, and minus 1 with respect to 4. Finally, we would get this in decimated order 0, 4, etc. So that's really very quick to draw, and I can draw that. Okay, so we have now transposed all the way up to here, and then these butterflies okay, and then leave first 2 alone, second 2 psi 8. I can put them back to psi 16 to the power minus 2 and minus 6. These first 2 are left alone, psi 16 to the power psi 8 to the power minus 1 and 3 are 16 to the power minus 2 and 6. Okay, so we are done with these twiddles, and finally last but not least, psi 16 to the power minus 4. And then these will be P0, P4, P2, P6, P1, P5, P3, P7. Okay, so that is that's the input now becomes the output. Okay, so that's all good. So far so good. I still am. I have one more task to do, and that is this. I didn't yet incorporate the n inverse. And think about this. What is n inverse? What exactly is n inverse? What is n? N, if there are m stages, in this case n is equal to 8. So n is 2 to the power log n to base 2. Okay, so n inverse is going to be 2 to the power minus log n to base 2, which I can write as 2 to the power minus 1 raised to the power log n to base 2. So all I really need to do is multiply 2 to the power minus 1 log n times. If n is 8, log n is 3, I have 3 stages. So multiply 2 to the power minus 1 at every stage. Okay, so that's one time multiplication. Second time multiplication, after every butterfly, multiply 2 to the power minus 1. And third stage of 2 to the power minus 1. And now we have included 2 to the power minus 3, which is 2 to the power minus 8. That's what is that. N inverse is that, multiplying by 2 inverse at each and every stage. Is that difficult to think about?
It's kind of weird.
It is. But, and let's just talk about why we are multiplying by 2 inverse instead of, well, first of all, 2 to the power inverse is one integer, okay? And here, 2 to the power inverse times psi 16 inverse, these two integers could be multiplied and take modulo q, and then this becomes really one multiplication. So this multiplication is one multiplication together, and so similarly at every stage, if you think about, half of them are twiddles, the other half will be 2 to the power minus 1, which will be multiplication. So why are we really doing all these things? I mean, so if you think about n inverse, computing n inverse, and let's say q. So in a lot of these, not in PQC, but in homomorphic encryption in particular, the q that we talked about is 400 to 500 to 800 bits. So that's the kind of, by the way, nobody really implements multiplications of 400 to 800 bits, and then you apply Chinese remainder theorem, and the so-called equivalent Chinese remainder theorem applied to polynomial operations becomes what is known as residue arithmetic. So that paper, the preprint paper, goes through all of that. We won't go through all of that here, but that's kind of the big, large number of Qs. So if I had n is equal to say 16,000, okay, so that means I would need 16,000, let's say this 400 bit multiplications. Okay, that's what I would need to do if I were to multiply n inverse for all of these n outputs. So I would need n qubit multiplications. Okay, so what have we accomplished by multiplying by 2 inverse? What's the advantage? So it turns out that the multiplying by 2 inverse can be implemented by not by a multiplication but by a simple add operation. Okay, so why would the 2 inverse requires one add operation? And so let's think about why 2 inverse requires one add operation. So let's say that we want to implement x times 2 to the power minus 1. If x is even, then x times 2 to the power minus 1 is x right shifted by 1 bit. So that doesn't require any multiply or add really. If x is odd, then I can write x is equal to 2 times x by 2 floor plus 1. 2 times x by 2 floor plus 1. If x is say 15, so 15 by 2 floor is 7. 7 times 2 14 plus 1 is 15. So I can write that as 2 times x by 2 floor plus 1. And then I can write that as mod of q plus 1 by 2. So that's kind of, x by 2. So x, okay. So let's just not skip that step. So that can be written as that times that. Why is that? Because think about whatever integer is here, if I take the modulo q, x modulo q, that this q thing will go away, the only remainder will be 1 times that. Okay, so x by 2 is going to be that whole thing divided by 2. And then if I multiply these and 2 cancels out with 2, we get x by 2 times q plus 1 plus 1 times q plus 1 by 2. Mod q, there is mod q, okay, there is, everything is mod q. And because everything is mod q, this q disappears because that's just q times something, you take remainder, that disappears. And so that says that this is equal to x by 2 floor plus q plus 1 by 2 mod q, everything is mod q. So now that says that if I take x, this thing is nothing but right shift by 1 bit, same thing. So I take x, right shifted by 1 bit, add to q plus 1 by 2, and then I have a multiplexer depending on the even or odd. We select if it is even, if x is even, select that, if x is odd, select that. So we need only one adder, modulo adder. These are all modulo, so one modulo adder. So now if I go back to the previous example, so I had log n stages, and every stage I need n by 2, right? So every stage, so I need n by 2, so this whole thing 16,400 bit multiplications are now replaced by n by 2 log n adders. That's our savings. So for 16,000, that would be 16,000 by 2, 8,000 times log 16,000 is 14, 2 to the power 10, 2 to the power 4, 14. So 14 times 8,000, so that's 112,000 adders. Okay, each 100, so if you think about the equivalent number of adders for 16,400 bit, think about 400 bit multipliers as 400 bit adders, 16,000 times 400, so this would be equivalent to 16,000 times 400 adders, and that would be 6.4 million adders. And now that's reduced to 112,000. So that's the advantage of multiplying 2 to the power minus 1 at the output of each and every stage. That's the savings that we get instead of multiplying an inverse at the very end. But anyway, that's the argument. Okay, so I think we have taken some time and gone through this modified, so negative wrapped convolution and the modified entity and identity. Hopefully that is more clearer now, and your homework doesn't of course ask you to do the 8 point, but that's asking to do 4 point. So since we drew these diagrams for 8 points, so if you look at the entity diagram, that I believe that the one that you are working on, and this is the 8 point version of that, which is here. I made a mistake. This is I entity. Okay, so if you look at the I entity, that's exactly here, 2 inverse and all these 1, 3, 1, 3, 5, 7, 2, 6. And so this is obtained by transposing and conjugating, or taking the inverse of the 8 point decimation in time. So I think what Sinway has drawn for the entity is this, but this is really the redrawn version. I wouldn't draw this myself. I would prefer that we draw this in the right way, using decimation and time, exactly as I have drawn here. Are you following me? Okay. But if you did indeed redraw this and reorder this, then that would be the same thing as here. Okay, so with that, I think I have completed this negative wrapped convolution. By the way, I should say that some of this is not our work, of course, and people have done all these, but I think the way that I've explained that is unique and different from any publication which I found, which are very confusing. So I have tried to explain them in a very simple way, but much simpler than any paper you would read. I heard Sinway tell me that it took me a long time to understand this. You can see that we can all understand this in 30 minutes. Okay, so any questions before I jump into the very last small part, and then we can start talk more about pipelining. By the way, the sample exam is now on Canvas from last time, but of course the topic that I'm teaching now is new and was not taught last time, so there will be one question that is not in that sample exam. Okay, otherwise I think that's a very good sample exam. Yeah. Okay, so the last part that I want to talk about before I exit this topic is the polynomial matrix vector multiplication. So now we are interested in multiplying matrix vector multiplication where the elements are polynomials themselves. So this is, by the way, if you look at the post-quantum cryptography PQC crystal Skyber algorithm, this is kind of a fundamental operation there. And what we are interested in implementing, let's say y is equal to a vector y is equal to a times, maybe I should use lowercase, a times r vector. So we have a matrix like A11. These are of course polynomials. Okay, so we are interested, and think about these. Think about these as a degree, and this degree 256. Okay, think about these as degree 256. Okay. So in this crystal Skyber, Q is 3329. So this can be implemented using 12 bits. 2 to power 12, 4096. So Q can be represented by a 12-bit integer. Okay, so one of the constraints, I mean, if we were to implement using entity with twice the size, that would be okay. So one of the things is Q minus 1 is a multiple of n, right? So is a multiple of n, and that's one of the constraints. I didn't talk about that, but that's kind of one of the constraints for implementing size n entity. But if you think about the negative wrapped convolution, what we are talking about here, and so if we did that, then Q minus 1 should be a multiple of 2n. and this q is not a multiple of 2n if n is degree or length, whatever length, maybe degree plus 1, n is the length, degree plus 1 is 256. So this q minus 1, 3328 is equal to, if I take this 512, that will be times 6.5. So it's not an integer multiple of 2n. So there are a couple of solutions. There are a few solutions. So one solution would be to increase q. We could increase q so that q minus 1 is a multiple of 512. We could do that. So that would be one solution. But the other solution is, instead of using 256 point entity or entity, we can just take the even and odd polynomials and compute using 128 points. So A11 R1. So for example, so Y1 is A11 R1 plus A12 R2, Y2 is A21 R1 plus A22 R2. Okay. So now what I could do is, by the way, this A matrix, there is no need to compute the entity of that. So we are now talking about, okay, let me say what we are trying to talk about. We are trying to talk about dividing these A11, A12, A21, A22, R1, R2 to even and odd polynomials. So now we are talking about polyphase combined with NWC entity identity. So that's our goal. Our goal is, how do we combine polyphase where we divide this R1 to even and odd coefficients. So I can then say that R1 2k, so this is R1 even, and R2 2k, that is odd. Okay. So okay, so R1 even, and then so instead of multiplying, so these are polynomial multiplications, that is equivalent to computing the product of the entities, add them and take the inverse. Okay, so A11 R1, so we take the entity of the even part, entity of the odd part, so using now the fast parallel filter. Okay, so one other thing is, in the so-called Kyber standard, these are kind of random polynomials. So if you take their entity, that would be another random polynomial. So in other words, we don't really need to compute entity of these things. These are just random polynomials. So this is of degree of length. This is length n by 2. This is length n by 2. Multiply these. So this is kind of a fast filter structure. There's no filtering going on. People talk about filtering, but So the filtering really now is just multiplying by this A11. So think about this A11 times R1. So we are now talking about A11 times R1. And so that is A11. So whatever is A11 in the equivalent frequency domain, so you can think of that as A11 even part. I'm not even writing down the whole thing. A11 odd part, and then this is even plus odd. I have to find some better notations, but this is not a filter. We can think about. So I'm trying to adapt the two parallel filter for implementing. So this is really the hybrid form. We have talked about polyphase based parallel multiplications, polynomial modular. We just finished talking about entity, and this is hybrid where we take the combined polyphase and the entity identity. Okay, so what was the polyphase here? This was multiplied by x squared, right? So in terms of the entity, so you can now think about this as multiplying this by the entity of, so think about now the product of three things. Product of three things is going to be, now this is going to be entity of 0, 1, all the way up to degree length n by 2. So this is n by 2 length. So you take the time domain, think about this as delta n minus 1 kind of thing, compute its entity, and let's multiply. This is n by 2 things here. Everything is n by 2. These are n by 2. These are term by term multiplication. This is n by 2. This result is n by 2. Okay, so so if we subtract this and subtract that, that is going to be here. Okay, that's going to be here. I'm going to leave it there. Okay, for a little while I'm going to leave it there. And then so if I did complete that, I'm not completing that now. So if I did complete that, that means just take this and add it here, and that would be the even part and odd part, and then we would compute A1 to R2. So then take the take these three things and then multiply by, take A1 to even, A1 to even plus odd, A1 to odd, so that times, okay, I made a mistake here, okay. Okay, it's not fully mistake, but okay, that's fine. That's fine. So this is still, so okay, this multiplication here is A21 R1. So that part is, so this whole thing, these three things are A11 R1, these three things are A21 R1, and I need similar circuits for A1 to R2, and then we need to add, okay, so R2 to K, R2 to K plus 1, and so let me just not draw the whole thing. So if we take exact same thing, entity adds exact same thing, and then what would happen from the R2 structure, we would get this product x squared. Okay, so the three things that come out of, like these three things, I'm not essentially drawing the whole thing, but think about these three things coming out from, this is A11 R1, and these three things coming out of A21 R1, these three things will be A12 R2. Okay, so then so instead of multiplying by x squared here and here, what I could do is, so that that entity can be multiplied by this by add and multiply. Okay, so that add and multiply. So this and that can be added and then multiply by the predetermined entity of the sequence 0, 1, 0, 0 and so on. In the meantime, the first and the first can be added, and then this can be added, and that will now be y1 even. Okay, that will be this y1 even. And then similarly, after we go through that, this and that will be y1 odd. Okay. Okay, it's kind of a bit confusing, but I think what the point I'm trying to make is in some applications we can combine the polyphase concept with the entity concept and then combine the two in a way where we can compute this matrix vector polynomials using certain parameters q and n, where the q didn't really meet the constraints of q minus 1 being multiple of 2n. By expressing this in terms of polyphase, the polyphase allows us to compute length n by 2 point entity, and at the end, by the way, at the end, I compute n by 2 point I entity. So this is 1, so this is cap y, and then you take I entity to get the final answer. Okay. So very interesting concepts, and again, as you can imagine, the whole post-quantum cryptography standards started in 6 years ago, 2016, and people have been working on these kinds of things all over the world. People are trying to, ultimately the goal is these kinds of things have to be performed at the edge device. So the e-commerce transactions and all other kinds of transactions will be ultimately replaced by something like Crystal Skyber. So there is all the industries. Intel is on it. Intel has been on it for a long time. Amazon, if you do Amazon Cloud, I believe they are making this available to you right now. So Microsoft is on it. Yeah, most companies are on it. So because they want to make sure their products are compliant with the PQC standards. Okay, any questions? I won't ask this in the exam. This last couple of slides definitely are not included in your syllabus. What I did teach up to the entity and the negative wrap convolution, that is, you are doing the homework, so that's okay. Any questions about these things? Well, I mean, if you think about what we have covered really so far, I mean, we started and spent a lot of time on FFTs, on complex real, and then we started from convolution, and then parallel filters. Convolution became a basis for parallel filters, and finally convolution becoming a basis for polynomial modular multiplication. And the polyphase concepts, the parallel filter concepts. So all of that, I think we have spent a lot of time talking about related concepts. So if you think about this class as really fast signal processing, and the word fast means reducing number of multiplications, and that's really been our focus. So our focus so far has been how to reduce the number of multiplications. And the remaining few weeks in the semester is we are going to deviate from that fast signal processing to high-speed signal processing. And high-speed signal processing means not just reducing the number of operations, but really increasing the clock speed and reducing the critical path, reducing the clock period, so that the clock speed and sample speed can increase. And there is a need for a lot of signal processing algorithms to operate at many gigabits per second, sometimes many hundreds of gigabits per second. If you look at the fiber standards at 400 gigabits per second. And so how do I increase the clock speed? So increase the clock speed means reduce the clock period, and reducing the clock period means reducing the critical path, and the critical path is the longest path to compute before the next clock begins. So what exactly is a path in a computing system? A path is any computation time from an input to a delay element from a delay element to output and from any delay element to another delay element. So if you compute all these possible paths, and the longest path is the critical path, so that's called a critical path, and that length of time to compute is called the critical path time, and that's a lower bound on the clock period, and the reciprocal of that is a lower bound on clock speed, and the clock speed is a lower bound on the sample speed. Clock speed is an upper bound on sample speed. So that's why one approach to reducing the critical path is called pipelining, and we alluded to a little bit, but we can talk about that in a more formal way. So pipelining is the process of adding delays. At so-called feed-forward cut sets. Okay, and it will take a little time to talk about these concepts, but so if you think about, I have some computation, let's say, okay, so let's say there are these nodes, this, let's say A node takes 1 unit of time, B node takes 2 units of time, C node takes 3 units of time, okay, for example. What are the path lengths? There is no delay here, so that's okay, so there are no delay. So the path length from this top path input to output, 1 plus 2 plus 3, 6 units, 1 plus 2 plus 3, 6 units, 2 plus 3, 5 units. So clearly the critical path is going to be either this ABC or that ABC. So both of those are called critical paths. Path length is 6. Now if I want to pipeline this to reduce the critical path, this is a cut set. A cut set is a set of edges which when cut it takes a connected graph and transforms that to disconnected components. So if I cut this edge and that edge, this is one part of the graph, this is another part, and they're disconnected. That's why it's called a cut set. And the so-called feed forward means the data on the two edges of the cut set are moving in the same direction. So basically it says that if I place a delay here and place a delay here, then I can reduce the critical path from 6 to 3. And that's the whole idea of pipelining. We call that a two-stage pipeline. This is first stage of the pipeline. This is second stage of the pipeline. So that's called two-stage pipelining. And in your homework this week, you are taking the fast parallel structures where there was a multiplication by x squared in the time domain, and then that was not implementable, and so we need to make it causal by creating a delay element there, and the way to create a delay element is to find a feed forward cut set and place that delay, and delay along with multiplication by x squared, for example, or x cubed in 3 parallel becomes a switch, and all other delays stay as they should. Okay, so that's kind of a brief intro to pipelining. So we'll talk more about this next class. I can stop here, and if you have questions about homework, we can discuss that after the class. I have your graded homework, so don't go away. I will hand them out also.
For this class? Yeah.
No, actually, I don't think I did.